Thank you, Mike. Thank you. Thank you. Good morning, all. Thank you very much for coming. The entire purpose of this presentation is that I think that the people like yourselves need to know this. I know some of you already do, but maybe some of you don't. And I do not want to leave this room before I'm sure you all have a very good and basic, at least basic understanding of these two topics. And I put this software 2.0. I don't think we get around to it because I hope we'll be interacting all the time. So there won't be much time to talk about software 2.0. So we need to have another PhD student examination so I can come back and talk about software 2.0. You all know what big data is, and you all know what AI is, sort of. But you don't. So we'll get to it. We'll get to it. Good. But the important thing is it's an introduction. So this is all, we have all these 4-letter words, but we also have a 5-letter word that I would like to introduce to you. So DNV GL, the company I'm coming from, it's made up of Det Norske Veritas, which is a Norwegian company, and Germanischer Lloyd, which is a German company. They merged, nothing to do with wind, it had to do with the crisis in the maritime sector, so don't worry about that part. I come from a company that's called GL Gerdesan, which was bought by GL, which was originally Gerdesan. And as you all know, I've also been here for a day or two, but that's a different story. So we are about 14,000 people. We are in 100 countries. And I think the interesting thing is we are owned by a non-profit foundation full of Norwegian sailor type people. So we are non-profit in the sense that we have to make a profit every year. So I don't know where the non-profit comes from, but that's how it works. So we do lots of different things. We do maritime, oil and gas, energy, business assurance, and then we have a group thing. Energy is the wind belongs to energy, and I sit in group in the research division. And of course we work closely together to make sure that's what I'm responsible for wind and solar longer term research in the company. So that's us. And now for the most important bit of this presentation, me. It's only important because there's an important point in the middle of this. So I've worked in wind for 30 years, which is true. And I've also worked in AI for 30 years, which is a lie. But I have done AI 30 years ago, but I'll show you just shortly. So I did this neural network, which was actually 30 years ago. That was before the internet, more or less. So how did you do that? So what you had to do is so this is part of my master's thesis, but it's from '92. But what you had to do is you had to find the books first. And then you had to find out how the hell do you program these equations, and then how the hell do you do that, and how the hell do you find a computer that can do it. And then that's what I did. So that's the important point, because now what you can do is you can download a program, for instance, called Orange. You can define your data. You can say, I would like to have these 4 neural networks, and I would like to do a prediction of whatever you want to do a prediction of. That took me half a year to get to my master's thesis. It took me 15 minutes to do it like so. So I guess, I guess the computer I was using was like a cubic meter big supercomputer, which is slower than my iPhone by a factor of 100 or something. So those were the old days. So that's the whole point. So we've come very far for a very short time. You'll see this network structure again a little bit later. But just to show you that a lot has happened over the many years, as you all know. So we're going to talk about big data. We're going to talk about AI and machine learning. We're not going to talk about software 2.0, I think. But you look it up and you find out how it relates to all of this, I think, and then some conclusions. But I need you to talk to me as well. So first of all, big data and AI are two different things. You don't need necessarily to do AI when you work on big data. You very often need to use big data when you work on AI, but you don't always use big data in AI as well. So AI, artificial intelligence. It's a few hours discussion just to define what artificial means and what intelligence means. So I'm not going to do that. Machine learning is a part of AI, which is the important bit. Good. We need to work together on this presentation. So if you're not kicking back at me, I'll be finished in half an hour or something, and hopefully we get a discussion instead. Good. So big data. Can you please tell me about your big data? Not big data. Not big data. Tell me about, this is the humiliation part. So tell me about your big data. Not big data. Sorry? Not big data. Come on, we have to embarrass you a little bit longer. Because I think what you're all talking about, you're just talking about a lot of data. So that's different, which is the important point. So big data is characterized by the 4 V's, ladies and gentlemen. So volume, you all talk, when you say big data, you think volume. Yeah? So big data is not just volume, because big data is also velocity. It has to come at you at like astronomical pace. So you have to it's like what they call like drinking from a fire hose. So you cannot sort of get all the data in one go, and it's gone. It's varied, which is where most people fail to think about this as the definition of big data. So varied means it's not just one kind of data. I'll show you an example. And then this last thing called veracity. Do you know what that means? I had to look it up the first time I saw this word. Native speakers would know. So natives. Yeah, so truthfulness. So there's like in this day and age of fake news and things, there's all your data can have a sort of like a truthfulness to it as well, which is important. And I think that the whole point of this is that it's beyond the capabilities of the traditional way we do it. Good. So when you leave, you need to be able to tell me the 4 V's of big data, including the third one, which is the varied. Yeah. Good. This is just to show you how it works, what the difference is between like traditional data analysis and then when you talk about the big data. So traditional data is what we all know how to do. That's what we're trained to do. So we know the models, we know the rules, we can explain, we can time average most time, and then it's processor bound. We can use it mainly on a few or one processor. That's the idea of our normal way of thinking about this. But big data, it's data driven. That's probably why it's called big data. It's pattern based. It's predictive, which our models can be as well. It's real time, and it's distributed. And I'm just showing you a little bit about what distributed means. But this is like a completely different way of looking at these things. Yeah. So we are normally very used to having an explanation of something. So the answer is 42. You ask why, and then you go, okay, because I did this calculation. But if you ask a big data analysis, why is the answer 42? The answer will be, the answer is 42. But why is it 42? Well, the answer is 42. That's what big data can tell you. So that's of course what makes it all a little bit hesitant and insecure when we talk about big data. Good. Just an example of how this would work in wind energy. Of course, SCADA data, as Jakob said, and many others. That's of course the important thing. But if you want to look at the big data way, you also need to look at the various. For instance, if you do predictive maintenance or something, you need to look at the maintenance logs, and you also need to, if in a grid scenario, you need to look at the regulations and the markets and things like that. So you have to sort of look at the whole thing to be able to draw the proper big data conclusions. This is just all the players in big data, and I don't know how interesting it is, and it's probably wrong and it's probably too limited, but just to show you that many people are doing many things, and if you can't see it, but you'll be able to see that there's you see the Teslas and the Apples, but you also see so many other people in there. So how does it work? Okay, I have to say one thing first. do not worry about the fact that there's no ham on the first line. It is not the point of this slide. Please. Okay, good. So what big data does, it takes all kinds of different ingredients, yeah, and then it distributes the processing. So one cluster would chop the bread, one would slice the green peppers and so on and so forth. And then at the end, it's aggregated. So like this is what MapReduce and things like that. So this is the idea. And again, don't worry about the ham. Okay, so this is how it works. So all the processing is distributed. That's the characteristic of big data. Good. That was the end of big data. What were the 4 V's? Very good, good. Start with the difficult one. And veracity, velocity, and volume. Good. Yeah. I don't, and it's again not the point, Mark. So don't worry. Yes, but it's a fake tomato. Yeah. Good. Next step is AI and machine learning. So we talked about AI, artificial intelligence, is sort of like this bigger thing. We talked about machine learning, but then I think it's probably a little bit difficult for everybody in the industry, and I think every person who is in this industry would have their own opinion about what is what. So AI could also be like classic models, because it is some kind of intelligence. And if you adjust parameters, then I guess it's there's some kind of learning in it. So it can easily be that. It could also be expert systems. The whole idea that people started all this by thinking, if I just write down all the rules of the world, then I will be able to be as intelligent as a person. Yeah. So that's the whole. That was one of the early beginnings. One of the first paths into this was like just write down all the rules. And actually, there's still now. Do you know the Mosaic project from the Allen Institute? No, they sort of like a crowdsourcing thing that you ask people, say, please type common sense things into my system. So a ball is smaller than an elephant, and so on and so forth. So all these things you need to put in, and then once 1 million people have done that for 1 million years, their hope is that then you maybe have come up with something which. But there's also Bayesian methods where you sort of like try to go, so like say, okay, I know this, and then if I get a new observation, I need to change my opinion about it based on the new information. So that's also the idea. But what I'm going to talk about is in here. So that's the machine learning bit, which is I'll show you what that is now. But just remember that both machine learning and artificial intelligence can be many different things, and you need to make sure you understand what exactly is the definition. So this is just a little bit of hype. So AI is the new electricity. Just as the work of Thomas Edison has helped build an electric powered society, it's now time to build an AI powered society. So many people think that this AI thing is important. And the reason why I thought I would talk about this for you people is that I think, I'm going to say it a few times, but I think that my hope and vision is that nobody, including all of you, would do much work without having an AI thing next to you. I'm going to come back to that, but that's sort of the idea. It'll be as important as fire and electricity. So now you know it's very important, yeah. And in case, if you haven't opened a newspaper for the past 5 years, you would have known this anyway. Good. So machine learning, what can it do? And I'm just going to show you like some basic things. So what it can do pattern recognition, as I talked about on the big data as well. It can do separation of spaces and stuff. It can be predictive, and it can generalize. So those are the things it can do. Very simple in some sense. And I think if you want to really think about this in sort of like a simple way, it's mainly just finding patterns in data. Yeah, if you have that right, then you won't be scared about using it, I think. Yeah, but so mainly just about doing that. So it can be done in 2 different ways. One thing we can easily understand, and one thing which is a little bit more difficult to understand, I think. But so supervised is where you have labeled data. So you say show the picture, and you say cat. You show it another picture, say cat. Show the picture, say elephant, and so on and so forth. And then every time it's done this, it can then classify these things according to what they are. It can also do regression. And this is now where we have to introduce the minimum 100-dimensional problem. So we can easily do regression on a piece of paper in 2 dimensions, yeah? We can easily draw the 2 axes, see all the dots, and then hide the most difficult dots with a legend, and then draw a line through the rest of the dots, yeah? That's regression. And that's easy for us to see as humans. But what we cannot do, and this is where these systems will help us, is that if you have a 100-dimensional space, it's a little bit difficult to draw these hypersurfaces through these data sets. And that's, of course, what these systems do effortlessly. Yeah. The way it's done is that you often train on some part of your data, and then you validate on another bit. There's a more fancy way of doing it now, which I'm going to grill Elliot about shortly, so I'm not going to mention that. But this is the basic idea. And then the difficult bit is
don't we actually help Google each day when we authenticate ourselves and they ask questions, so like the parts of the picture which have signs?
Yes, that's right. Yeah. Show pick the pictures with cars, or whatever they do, and then you say, and then thank you Google, you've now made money on my work again. Yeah, that's right. Yeah, so that's supervised.
Yes.
Unsupervised is that basically what unsupervised does is it can cluster data, and it can reduce dimensions. Yeah. So clustering means that in these, you have to think 100 dimensions again, minimum. So in this 100-dimensional space, there are some certain clusters of data which are similar in some kind of sense of the word. Or you can say, okay, you have shown me 100 dimensions, but I can make that into 5. Well, thank you very much. I don't understand 5, but I guess it's better than 100. Yeah, so that's the dimension reduction. And we know this from principal component analysis and things like that, which is one of the tricks. So that's the next big thing you need to remember about the machine learning: supervised and unsupervised. Supervised, I think we can understand. Unsupervised is difficult. But that's, of course, you see that in a lot of cases. These are some examples of supervised, and you'll be very happy to see that this is a like simple regression. Again, not 2D, but 1552D. I don't think I need to go through them all, but you'll see there's something. We have the Bayesian stuff as well. We have the most famous ones, which we're going to talk about later today, is neural networks. But there's a box 3 at the end. So what we normally do, what we have learned from our modeling in the classic modeling, is that we always do combine these models. And of course, that's the way forward also in machine learning. So don't forget all your old tricks in the book. You still need to make sure that you understand how to deal with models and stuff. And the whole problem of machine learning is not to get the code. That was my problem in the old days, because you had to write it yourself. But now you can literally download this in less than a minute. So the whole problem with machine learning is not the code. The whole problem is which code for my problem. And the second problem is, how do I tune this particular model to my problem? And the fancy term for that is hyperparameters. That's the other thing you need to remember. So you need to understand the hyperparameters, and you need to understand what kind of model to use for your specific problem. And again, this about understanding which model you can use is again very simple in many cases, because you have all these user interfaces, and you just say, I don't know. So you just plug all the models in and see which one does best. That would be a first start for that. So that's sort of the idea. When we use the unsupervised, actually the deep learning algorithms are also used for supervised, but they can be used, deep learning and the dimensional reduction we talked about. So from many dimensions to at least fewer dimensions, that can be done automatically by looking for the patterns. Okay, so far so good. Okay, so this was the simple part. It can get a little bit more complicated. I don't know if you, has anybody not heard about Watson? You have all heard about Watson. Good, good, because then that means I don't need to explain this, and I can pick any person at random who would then tell me what this is all about. No, don't worry. So it's always, I mean, it's easy enough to choose the model to use, but there's a lot about, and this is also this thing about software 2.0. It's also about how you put everything around it, which becomes much more important now. But just to show you that in 15 seconds it can read like 15 million papers, and it can not only read it. I mean, I can probably be done in many ways, but it can also understand in the sense that it can draw things, lines and connections between things we didn't know. For instance, I think an example is that it found out that some kind of cure or way of treating malaria could also be used for cancer. Nobody knew that, but Watson said, do you know that if you do this, you can do that? And that's sort of like things we cannot see in these many dimensions, so therefore that's what it does. And I think you know where it's used already. They're not so successful, I think, actually. I think they would have loved to be dominating the world with Watson, but they're not really. But but you see that they can be in healthcare, teaching assistant, and Jeopardy, which is the most famous example, of course. But of course, this is now we're going to the darker side of all this. So unsafe and incorrect cancer treatment came out of Watson as well. So we need to be really careful, which is the third, maybe it's the fourth important bit of all this I'm saying. Yes, that's true, yeah. So local stuff, localized stuff, yeah. They bought, it runs, what's it called? The Weather Channel. IBM bought one of those big, and they put Watson underneath. So, first question, it's not a question for you, I'll show you the answer, but so can a machine learning system spot wind turbine faults, for instance? And then this is something that I'll show you some work we've done. So this is like a condition function, which we managed to get beat into one dimension from I'll just show you how many dimensions we use. So we use like I think 10 dimensions or something. So taking all these 10 dimensions, we managed to put these into one, so like condition function. And then if you were watching that as time went by, you were able to say this is the time where this condition function starts to misbehave. Therefore, we know in advance that something is going to break down. And the way this is done is in this particular case we used a support vector machine, which is one of them, like trying to draw hyperplanes through your data, based on all this. This is like you recognize this, and you see this is not big data, of course, but this is just a lot of data, and in this case we only need a lot of data. So, but it's still varied somehow. But it's like all kinds of different things, and it came out with that. So that's one example. We don't know really how all this is combined. Of course, you never know that, because there's probably, I don't know, maybe 1,000 different parameters in such a model, maybe more, which are just then trained and adjusted to fit this particular case. So we don't know how it works, but we can very clearly see that it works. Okay, can we then get neural networks to understand physics? And ladies and gentlemen, I have made this example for you today. So what kind of physics would be interesting for all of us? Well, I thought the logarithmic wind profile would be something interesting to learn about. So I made 10,000 data points of random, correct but random combination of roughness U star and Z, and then output was U. and then I used 4 different neural networks, and this is what the data looks like in 3 dimensions. A complete mess. So this is a Z and U star and height, I think. Something, no, U. Anyway, so this is only the 3 of the. I couldn't get my program to plot a 4-dimensional thing for you, so it's only 3-dimensional. So again, this is then what I did. I took this into Orange, and this is I think the important bit about this as well is that you can play with this. You can play with it, and just go and do it. Get your data and play with it. And then I just these were the 4 models I showed you before. So like 4 different neural networks. And then we just did it, so don't worry about the numbers, but you can see that as these are the less complicated one, and this is very complicated. As you put more and more neurons into this, all the error measures reduced. And just to give you a feel of this is probably the simplest neural network we can think of with only one. This is the input, this is the output, and this is the learning bit. And you can see even with only one neuron, it sort of can get the pretty good. I know some of you know about neural networks, and I guess you can guess why it works so well, relatively well. Yeah, no uncertainty first of all, but why is it easy for a neural network to figure out the logarithmic wind profile? The activation function looks this is a technical speak, but it looks very much like that's why it's so easy with only one neuron as well. But you can make it, as I increase the layers and the number of neurons, I can make it better and better. This is a complete and ridiculous overkill to do this, because I probably almost have more parameters. But you just see, as we go through the complexity, it gets better and better and better, and a much deeper understanding of how this is. So some thoughts. This was sort of the technical bit, I think. So machine learning, 2 different things. 2 different types of machine learning systems. One is supervised. Oh, you're very good. You see, only before noon. Good. And the other one was unsupervised. Good. And the important thing about choosing your model was, first of all, to choose it, and then secondly, thinking about the, can you remember that difficult word? Hyperparameters. Good, good. So that's the whole thing. Now you are almost ready. So this is so you know this MIT Technology Review. They came out with this, they asked 97% of workers think it's unlikely they will lose their jobs to automation. It will soon be obvious that half our tasks can be done. That's a different number than the 94, which actually what people think. This is Kai-Fu Lee. I think you know him maybe. I can't read this one. Something with 100,000. What does it say? Amazon. Yeah, there you go. So already now they have, and there's sort of like every 2 months or something, there's a story about the poor workers who are being outpaced, outgunned, whatever you have about robots. There's Amazon. So what do you think? And of course, the most interesting question is, what do you think about your own jobs in this context? You do not need to answer that, because that will probably be not so nice on a Monday morning, but I think it's probably worth thinking about. Yes, yes, yes. And I guess this is an example from our own world, which I'm just showing you here. So we had a project. My group had a project. We had these. You probably know them because I've done them when I was a researcher. These bankable energy reports. Yeah, and they took. Normally, when we do it, the current way we do it, it's like 4 weeks and a bit. And then what we did was that we looked at how everything was integrated and what the decisions made through the process were done. And then we focused on one bit, which was this bit here, which we managed to get down to this size. So instead of having an analyst work on the data for more than a week, by using these different systems put together, we managed to get that down to half a day or something. And now I'm going to introduce a terrible Silicon Valley term, 10x. We're gonna 10x this, guys. Do you know what that means? So, in the good old days, when you came and told your boss, I have improved my processes by 10%, the boss would say, Lars, that is really good. 10% is fantastic. If you do this in Silicon Valley, they'll throw you out all the way up to Seattle, probably. So now you need to 10x things. So that means every time you look at a process, every time you introduce machine learning, you need to make it 10 times better, faster, more efficient, cheaper. Yeah, that's the idea of 10x. So you need to 10x things. So, and you can see we managed to do that easily in this particular example. And of course, the idea is you can see that some of the boxes are then been increased, of course, and this is this is a very good example of this discussion about how when you automate and do things. So what the hell are we going? If we can 10x everything, so that means I count 1 out, 2 out, 3 out, 4 out, 5 out, 6 out, 7 out, 9 out. You're in 1 out, 2 out. So what will we do with these 9 people? So what the hell will we do with 10x? Why is that interesting? Of course, the interesting thing is that it's not all the processes you can 10x, so that Andrea was saying. You can find the clever bits, and you can spend more time on those. And that is what we then ended up with in this system, that we compress some things, but all the interesting bits for the analysts we could do longer, make longer. Yes, 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 exactly, yeah. So it's exactly, yeah. So it's like it's new. That's my point of this whole thing. It's our new helpers, and we need to do them, because if we don't do them, our competitors will, and therefore we're in trouble. What's he called? What's he called? This guy, this old economist, the Scottish guy. What's he called? Was it Adams? Yeah, possibly Adams. He said that looking at the productivity, this is like 200 years ago, looking at the productivity gains we see now, it would be ridiculous to think that we would need to work more than 15 hours. Our grandchildren would need to work more than 15 hours. That didn't quite happen. But so it happens every time efficiencies come about. People will need to do other things to get busy. And always, if you want to explain to somebody, even to my parents' generation, that what I do is I design web pages. Go back and eat your potatoes, boy. So that's like so it's everything changes. And of course, the big discussion is that is this time different? So is this time different when the agricultural revolution, everybody didn't need to work in the agricultural businesses, but they could go in industry. when the auto service industry happens, we could automate industry, but then we had the services. Will this happen again? Will there be something when we now automate the services? What will help us with that? Was there a question somewhere? Yes, yes. Yes. Continuous learning. Yes. And UBI is also something. Universal basic income is also what people think about. I think that's another discussion, but it's on the slides shortly. Good. So we just put out, not just, but we just sort of recently put out a position paper. Don't worry about all the stuff, but the second bullet is probably the most important bit. Of course, it's coming to renewables. We've seen it already, but also that you have to have this you can download it for free in the usual internet sense that we want your email address, of course, but otherwise it's free. But the idea here is that we need to always think about the tedious tasks, the extra analysis we can do, and have somebody else being the AI system do that for us. I think that's the whole point of all this. So you can read all the stuff there as well. This is just, you don't need to worry about that. It's like digitization. I don't know. don't need to worry about that. But just to show you that many people think a lot about, you know the steps to get to AI. First, it's to digitize, meaning put things into digital information. Then it's to digitalize, meaning use the processes, the strategies around how to deal with digital information. Then you need to automate, systematize, and then you can AI-ify it in the end. So everything needs to start with digitalization. So I just want to show this funny example. Do you know this adversarial patch? Okay, it's quite funny. Okay, what is this? This is, we should ask a classifier, a banana. Very good. It's maybe a slug, but I'm pretty sure it's a banana. Okay, so what I'm going to do now is I'm going to put a psychedelic picture of a toaster. Is that a toaster? Can you see the toaster? I'm going to put that next to my banana. Nothing unusual. What is this a picture of? To you guys and girls? A banana. Yeah. However, this system is 100% sure it's a toaster. Maybe it's because there's more colors, there's more things happening, I don't know. It focuses on different things. This is just a word of warning. Any idiot can see that that's a banana with something funny next to it, except for the system we will have driving our cars. Good. So you can actually just the algorithm that can generate these psychedelic things for you. So don't worry about this. We just talked about it. But I think this one is interesting. We tend to overestimate the effect of technology in the short run and underestimate the effect in the long run. Yeah, maybe. Yeah, maybe. Yes. Good. So as I said before, we want the woman and the machine to work together. Okay, so how do you want to start? I can see we're not going to get to the software 2.0, so we just so there's, as I said before, there's like a million different ways you can do this, and if you can't program in Python, you're out. But actually some of the TensorFlow is now in all kinds of different things. But these are just some examples, and this is the only slightly advertisement from DNV GL that I have here. We have on top of Azure, we have put this thing we call veracity. So that's not why everybody in DNV GL knows what veracity means. So this is an industry data platform where people can put, including you, can put data, and your clients can put data, and then the client, or you can say, you and you can use this, and this is the application you want to run on this, and it can run only on these data, and these people only can see these results. So it's like a safe way of doing this. That's end of advertisement. But as I said before, what I used this for the example was this Orange, which is free, runs on the PC, easy. So do you all know Orange? Go and download it and go and play with it, please. You'll see lots of interesting things, and it's very easy, and it has all the machine learning algorithms ready, just to drag and drop, and then you. That's probably the services which are very difficult to do, but these are just examples. Yeah. Good. So this is just from the thing from the. So we won't get to software 2.0. So I'll just you can look while I flick through the slides, but this is sort of like what the idea is. So we talked about big data. Will we do it again? Varied, veracity, and velocity. Yeah, good. We talked about machine learning, which was a special and very posh part of AI. And we had two different types, which we understand, and oh, you're so good. Oh, I'm so happy. Good. You do have no clue about software 2.0, but that's okay. and then we talked about conclusion. So we talked about the log law and reporting and gearbox failures to make it a little bit more wind energy-like. We haven't talked too much about robots and things, and we talked a little bit about disruption. And there's a whole day's seminar on superintelligence. People say that the most optimistic people, or whatever they are, I don't know if it's optimistic or what they are, say that in 15 years we will have intelligence, artificial intelligences, which are more clever than us. Looking at the person next to you, you can understand why that's possible, but looking in general, that might be a little bit more difficult to see. And this is where we're going to talk about ants. Ants. When you walk from here, from your office to here, how many ants did you think you stepped on? Probably quite a few. Are you evil towards ants? Some people are, of course. The bizarre ones are evil to us, but most of us don't care, unaware, uninterested, unless you're Buddhist and you're really into it. Yeah. So a superintelligence might consider us as we consider ants. It's not evil. It's not the whatever it's called. What's that net called? Skynet. It's not Skynet kind of thinking. It's just uninteresting. I have my goals. I know what I want to do. And humans. Okay, I just step on them because I'm going there. So that's the scary thing about superintelligence. Of course, we talked a little bit about safety, and we talked a little bit about. I pointed the 9 out of 10 out who would be out of work. Yeah, good. So now you can also play AI bullshit bingo. Thank you. We have 2 minutes for questions, I guess. Yeah. Comments? If I knew the answer to that, I would. What do you think? Yes, yeah, you can use the platform, but I think there's still. I mean, I don't think all universities should start developing new machine learning algorithms, for instance. I think that would be silly, and of course, this is another example of winner takes all. So only the best universities in America and China will do this, whereas everybody else trying to meddle with that will be losing. So I don't think. I think it's so. So I think that's probably where the software 2.0 idea is. That so what you need to know about, what you need to think of, is the data. So and the data and the structures around the data, the learnings you can then and the latest trend is also like people refuse to accept that neural networks only gives answers and no explanations. So also with deep learning, this thing called deep, people are now trying to understand what is it the different layers do, for instance. So like this guy detects edges. Okay, this guy detects 3 edges together forming a triangle. This one is a circle. And with the proper number of triangles and circles, you have a cat kind of idea. Even if you turn it, this guy understands the rotation, and I can rotate it back. And so we are beginning to understand a little bit the deeper bits of. But I think the interesting thing for us, who wanting to do research and science, is to see if we can prize the information out of the knowledge, the understanding out of all these systems. But yes. That wasn't the point. Exactly like the point about the ham not being in the was also not the point. No, it's just to show you that it's simple pattern recognition. That was. Yes, maybe, yeah. I think IBM Watson would say by using IBM Watson for that, but I'm not sure. I think that's the right, and I think as we all know, it is already a chaotic problem. So you cannot even with machine learning, you cannot look into chaos. So of course, so it's like I think what we used to call model output statistics in the old days, but like we see more and more people build more and more both on the actual streams, but also on images, weather images like the pressure, the whole pressure field, the whole temperature field, the whole satellite pictures of clouds, combining all those things with image recognition and moving things about with these LSTMs, which we're going to talk about later on as well. I think it's safe enough, yeah. But I mean, us in business, we need to make sure we understand that everybody, all our competitors will start using machine learning. The smaller the company, the quicker it can move to using these things. We'll be slow because we're big, and if we don't follow the trends anyway, we could easily say this example I gave you with the reports. We don't need to do that because everybody knows us and everybody's happy to pay us work for 5 weeks on this rather than 3. But all of a sudden, very slowly, it's getting eaten away. Yeah. Yes. Yes. But again, understanding, I think what we have, like we had 10 dimensions. Understanding something in 10 dimensions is still quite difficult. Yeah. I think, are we being thrown out, or do we need to stop, or? Yeah, okay, one more. Yeah. Yeah. I think many managers would think that AI the management would be the last thing that AI can conquer because it's so difficult that it'll be impossible to replace the managers. But I don't know the answer to that question. Yeah. Supervised learning. Yeah. I don't think I know how to answer your question. If it was a question or a comment. Yeah. One last one.
Are you sharing the PPT?
Some of it, because some of them I've stolen from different places I haven't got permission to. Yeah.
It's rather a comment. It seems to me that what you really can get from that's the ability to something collection, large, huge collections of data, which seems completely unstructured.
Yeah.
Then this could help us to see, well, if you look at it from this direction into the space, then suddenly you can see what matters.
Yes. See in the sense that we can't see it, but we know that the machine learning system can see it. Yeah. Which is difficult. Yeah, but that's right. Yeah. Good.
Thank you.
Thank you.